Hello and welcome back. In the last I/O video, we added SD card support to the existing SPI circuit, and that added the interesting feature of storage to the build, and I'm looking forward to experimenting more with that. But for now, I want to kind of compress the build down a little bit and convert those breadboards to a PCB. So let's look at what we need to do. Okay, so the blue PCBs are the core CPU, and over here we've got the peripheral circuitry. We've got the UART, the sound system, the SNES interface, and this purple PCB is where I want to put the SPI circuitry. This currently exists on 3 breadboards. We've got the MCP GPIO extender, we've got an RTC clock, and of course we've got the SD card. Now, the overall chip count here, this shouldn't be a difficult translation to this size PCB, but we've got a battery and we've got a SD card socket, which are going to take up a little bit more room on that PCB. Down here, we've got the chip select lines and we've got 5 unused ones. So I think it would actually be quite nice to have 1 or 2 headers on the PCB that brought some of those out, just so we could do some experimentation with other SPI devices in future. Most of the time when I design a PCB, I've got a rough idea about the space it's going to take up in the final build. But in this case, I've got an exact form factor for that PCB because it's the only remaining space in that peripherals backplane. So let's hope I've left enough room to do what we need to do. Let's take a look. So here's the backplane, and here's the gap we've reserved for the I/O board. Now we basically brought all the connections out we thought we could possibly need. And I also created this little PCB that we plugged in on top temporarily that creates those connections out, which is what we're spending most of our development time for the I/O board with connectors plugged into. Now the oscillator that we put here we'll need to do something about sooner or later, but I have done some work on the peripheral schematics. So these are the inputs we've got on that board. I've also got the schematic here for the SPI work we've been doing, as well as the real-time clock connection, the MCP GPIO expander chip, and the SD card, which is the last bit of circuit we added. So I think what I'm going to do here is create a duplicate of this so I can keep this circuit. So I know this is going to plug into the backplane okay. This does look like quite a lot to fit in that space. Let's see what we need. So I know this is going to want to go at the bottom, or at least on the edge somewhere, but the bottom is going to be the most reliable place to access it. Okay, that doesn't look right. Now that's the CR2032 battery holder. I'm going to temporarily move this circle around with it because I don't want to put anything inside that space where the battery is going to overlap. Let's see if we can separate this all out. RTC chip is tiny compared to a lot of the others. I need some decoupling caps for these chips as well. Those are the ones on the 3.3 volt rail for the SD card. Now I've got 5 chip select lines currently being generated that aren't used. That gives me a nice SPI expansion header. I think I'm quite tight on space. I'm not sure if I want 5 of these duplicating the lines. Let's get a big capacitor for balancing power on the input, and then we need decoupling caps for everywhere else. And this one already has decoupling on the output of the power rail where we generate the 3.3 volt. Not sure if we want anything on the input to that. Though I don't think anyone's ever commented saying I've got too much decoupling, so I'll stick it in there. I've already got one, that explains that. Alright, so we've got 4 chip select lines we haven't touched, and reset, clock, and dev10 load. Those are just inputs to the main board we haven't used in the circuits. I'll tidy those up later. I'm going to try and stick that there. Main bus lines are going to be a lot easier to route. Now some of these need the main bus as well. which are the input and the output shift registers. Right, so the crystal I selected had a requirement on the data sheet for the 9 picofarad load capacitors. Hopefully I've read that correctly. I'm going to keep that as close to the RTC chip as possible. This feels a little bit tighter than I thought it was going to be honest. Okay, I'm starting to feel a bit more comfortable. Now the outputs from each of these should go to a distinct pin. These resistor arrays are not doing us any favours. Now I've got the 4 resistors that pull up to VCC, 5 volts, on one array, and the 4 that pull up to 3.3 on the other. But just looking at the way this circuit works, I think we want to do it a different way than that. Okay, that's completely the wrong thing. So MISO, I want to be the far end of the other array. And MISO 3.3 the next. That's better. So then clock in the same pattern. Mozzie. And then chip select by a process of elimination. That should be quite nice to fit the power regulation down in the side. Now that's one spare SPI header. It's always worth looking for a good spot to put the JLC serial number that isn't going to be visible on the final PCB. Sometimes I think I'm tempting fate by putting version numbers on stuff. So I'm thinking if I put a little header with these 4 chip select lines on it, and have a full header with everything for one of them on, in the unlikely event that I want to attach multiple SPI devices for a piece of test work, I can have headers connected to each of those. Not using that. Now I do have reset lines on the RTC and on the MCP device. I've never actually tested they work with that reset signal. I'm going to play it safe. That's the system clock which we do use. The UART clock I don't need. Although the sound device and the SNES controller interface need the UART clock, so I do need to wire that out from the UART board at some point. I think that's going to be a simple update to that PCB. Okay, well, everything that needs to be there is there. I think that's going to look really nice, so nothing left to do but start routing it. Okay, as always, I'm going to hide VCC and ground. We'll come back to those later. Our datasheet did strongly suggest that nothing be underneath this chip apart from ground. So I think I should probably obey that if I can. Definitely worth putting the effort in to make those lines neater. It felt like I was saving some routing space by going around with those GPIO lines on the top layer, but I've got to get these lines elsewhere in the circuit. It'll be easier if I just use the bottom side for each of these as well. Now here's a concern. This is the system clock line and it's going under the battery for the RTC. No idea if that's a problem or not. I think those two might be easy the other way around. That's not right. These are unused inputs, and my intention was to bring them down to ground. Right, so that's all the signals done, which has got power and ground to do. So now we unhide VCC and ground and see what we've got to deal with. And that is fully routed. This is going to be an awesome looking board when it's done. It's such a lot of features being added to the system. So with all the DRC check errors complete, we can start the process of having it made by selecting this Generate PCB Fabrication File option. And if we're getting it made with JLC PCB, it's absolutely trivial. We just push that button. Now let's look at a couple of options that are very important to remember. You can obviously change the specification of your board, but this remove order number 1. Now that means the serial number on the board will move to where I specified with the text box saying JLC, JLC, JLC. I don't want PCB assembly, but I do want a stencil. There's a set of sizes here. Now we can specify a custom size. This doesn't affect the pricing at this stage, but these large full-size stencils, they cost a lot more to ship, so it's always worth dropping the size of it if you don't need the big surround for a fixed size frame. So with the stencil, $14. So I got both the PCB and the stencil. It's a really nice board. Slightly clipped to a corner there though. Now I should mention that this video is sponsored by JLC PCB. Now some people will express surprise that I wasn't already sponsored by them. They can design a PCB like this so easily online and then just send off and have this arrive a matter of days later. In fact, it was seeing the PCBs made by JLC PCB on Julian Eilett's and the Unexpected Makers channels that added to my whole idea to make this entire build. Now, the core CPU is something like 20 unique PCBs, all of which have been made by JLC PCB. So in actual fact, you've seen me take PCBs out of one of these boxes many times. The Peripherals board is another 10 PCBs-ish, and the VGA circuit is around about the same again. Obviously, there have been various duplicates at times because inevitably I make mistakes, so there isn't one on here. So I can't tell you if this sponsorship will go on or be a one-off, but the sheer number of times I've unpacked a PCB that's been made by JLC as part of one of my videos, I think that goes to show that I'm actually very happy with the standard I get from them, and it's a big part of how I feel I've been able to put together this entire build over the last few years. Let's see if it works. Now, these resistor arrays and that RTC chip are the ones to pay close attention to. The larger parts are very forgiving. What I'm going to do is try and provide a little bit of downward pressure just to reduce the gaps. Okay, I don't like that. Trying to lift it up, I twisted it slightly, which is not good. It's probably fine over here. And of course, if you don't want to risk mistakes like that, JLC do offer a assembly service. It's not perfect on those tiny pads up there. Let's hope the reflow is forgiving enough. Now these boxes JLC send are actually quite useful. I've got dozens of them lying around that I use for part storage. Now these capacitors are 0603 parts, as opposed to the 0805 I use for a lot of stuff. This is the crystal. I could have positioned these labels slightly better, but it's the two lower ones are 100 nanofarad. This one on the 3.3 volt rail. I normally only have one of these on most boards, but here I've got the separate 3.3 volt power rail. So both 100 nanofarad and a 10 microfarad on there. These are 10k resistors as pull-ups. Right, so that's the SD card and the RTC circuits, minus the RTC chip. Now, I originally bought two of these and then lost one, so this is a replacement part. Right, let's get it round the right way. I do not want to be manually reflowing this. Now the solder will move away from the solder mask. So what I really want to do is make sure I've got the right pins lined up. '86 is a set of exclusive OR gates. 253 is a multiplexer. We use that to switch which clock source we're using. And the 595 is a shift register. This is used for reading the data in from the SPI devices and converting it to a parallel signal for our main bus. And the 165 is a parallel in serial out shift register which goes the other way. Made a bit of a mess of that, but I think it's okay. And this is the 138, which is the 3 to 8 line decoder that we use to generate the chip select lines. In my very early soldering videos, I used to think these devices were tiny, and they look positively large now. Now this device, it's got holes in the board that should line up with some feet. The registration on that is quite reassuring. It does occur to me that this could go completely the wrong way around. There is a plus there, which is aligned with the plus there. Now this circle wasn't part of the original symbol. A little bit worried there's not enough solder to flow onto that pin, but we'll see what happens. Okay, let's get set up for reflowing this. This is a nice looking board. These caps look fine. Looks like a little blob of solder. Okay, that looks like some solder bridging there. And a bunch over there as well. So the slightly smeared out solder paste is a problem. That looks good. That's got it. That looks alright now. Already looked at all of those. A couple of little solder balls collected up on these as well. Nowhere near making any electrical issue though. Do have a couple of solder bridges there. Right, that's all good as far as I can tell. Now we've got some headers for the GPIO lines. Right, I was going to do this with a female connector, but I've had a rethink. I'm going to go with the exposed header pins. I don't suppose it matters much either way, but GPIO pins on most modules are normally male like this. It'll make it easier moving cables around. Should I do the same for these? Nah. Okay, nothing left to do but give it a try. Let's have a look. That's going to fit in that space nicely. Now there's 4 separate circuits on here, so I'm kind of bracing myself for some kind of a problem. Guess we power it up. Okay, nothing's gone horrifically wrong. Okay, well, that's not good. So that's the first capability we've got, is the GPIO device. Let's check other devices. Okay, so obviously we have no battery and we haven't preset the time, but that's showing 2 minutes and 6 seconds. Okay, I feel a bit better now, because the RTC circuit is working, and that means that the main SPI communication must be working. This old kit logic probe is getting a bit tatty now. I need to replace it in some way. I wondered if the LED output was wrong. Have a look at the SD card. Okay, obviously errored straight away. But that's not working either. Right, so there's 2 possibilities here. I've made a mistake converting the circuit over, or I have made a mistake on the soldering. I'm just trying to think how we can go about trying to diagnose this. Got the bus connector on the wrong way around. It is not reversible. Right, so what I've done is I've shadow connected everything, so they should do the same thing. But I'm going to pull the assert line high, so this shouldn't actually push anything to the bus. That's interesting, I expected that to work. Okay, I've written a very simple program here. It's going to output FF to SPI control. So we're seeing all the ones here. So we should be able to pick that up on this chip here. I've manually edited that to be a 0. You run that and all the LEDs go off. Well, that at least works. So on this extra board, that's chip select 11. This is active low, so when it's not selected, it should be high. I believe that's the bit pattern to chip select that. Yeah, that does change. I'm curious to know why the MCP device doesn't work. Its chip select line is the 3rd pin along, and as expected that's high. Right, so the chip select line is working. Now, these headers for connecting bits up are actually going to be quite handy for this testing process. So, there's the ground, and there's the clock. That's not the cleanest clock signal I've ever seen. So in theory, the purple trace should be the clock going to the MCP device here, and that's the clock device on that board. I've been having trouble with this scope probe. The clock down here is a bit funny, but it's above the threshold, it should work. And that's Mozzie. That's interesting. I'm seeing master out here, but not over here. So I've connected the purple trace to just the load line. That's for the control. That's the load line for the data. This is me diagnosing why this isn't behaving right. I'm not even worried about this at all at the moment. Let's take it from the source. Still getting nothing. Interesting. Now, I actually made a mistake here and I forced the read line, not the write line. So you had a bit of bus contention there. Right, so that is now appearing how we'd expect. The data lines also match, or do they? That's very curious. The data lines don't match. Oh no, that's it. These 4 lines are the wrong way round. So that's an error transcribing the circuit from the breadboard into the schematic. A simple mistake that's going to cost me a lot of time. This actually explains why the RTC works, because the RTC read operation is doing sequential reads from address 0, and of course 0 doesn't matter if you've swapped some bits around. It's that chip there and 4 lines that are problematic. So these are the GPIO commands for messing with the MCP device. That's what we've been doing from the command line. So as a test, I'm going to write a version of those commands that swaps the 4 bits before sending. CB write, it doesn't have anything in the lower 4 bits, so that's not a problem. So I don't actually need to duplicate this out at all. OLAT and IODIR. IODIR is 0, so that's not a problem. So the correct bit pattern is, so we want to read the bottom 4 bits in reverse. So that's what we were seeing. Bingo. Okay, that gives me a lot of confidence. Okay, so just to explain what I did there, it was only a very small amount of the data written was actually affected by the bottom 4 bits being swapped around. So for the MCP device, I was able to just write a modified version of the function that would output the data we need to get the correct values to the MCP device. It's just 4 lines there that's wrong. Question is, can I bodge it? Now, obviously I need a new PCB, but if I can bodge this, I can test the rest of the circuit as working, and it stops being so urgent to get the new PCB. As these 4 wires need to be transposed, and I see a few choices. I could lift the chip off and cut the traces and then fit wires to the pins, or I could just lift the legs up and wire to those. Now this one is actually the one that I could cut the track if I needed to. This is not as easy as it was in my head. Wait, have I snapped that off? Or have I soldered it back down? I think I've snapped it off. Okay, well that felt quite easy. Now I just want to lift any remaining solder off here. That looks good. At the behest of people after my last bodging effort, I've purchased one of these craft knives. This first wire we've actually got loads of flexibility on the cut for. Feels like an awful lot more precision than I had with the previous knife. Interesting. That little craft knife has severed those tracks easily. Not sure I trust it anyway, but a second good place to get at them across there. If I do that, I'm hoping it will limit the chance of accidentally rejoining them with the soldering. Then that's total overkill. So it's the middle 4 pins here. Right Right, I think I have successfully bent up the correct 4 pins there. I need to solder it back on. Now all I need to do is not knock it off when I do the next one. Right, so by far the easiest place to attach these is to the bus incoming connections. None of that is pretty, but let's give that a test. This is a very nasty looking bodge, but if I can make this work, it's going to save me a lot of hassle. Fabulous. Oh, that's cool. Okay, had to go hunting for the right SD card. And there we go, we can still read data from it. Oh, I'm really pleased. Obviously, I'll be doing a fresh PCB. This bodge looks absolutely terrible, and I wouldn't like to rely on it too much. But we can take this whole bit of breadboard out. Well, I'm glad we got that working. Sometimes actually troubleshooting a board and finding the problem, bodging it, getting it working, and sending off for a refreshed PCB can actually be a little bit more rewarding than just having everything work first time, but it is nice when that happens. Hope you found it interesting. As always, I'd like to extend a big thanks to all my supporters and patrons, and of course a special thank you to JLC PCB for sponsoring this video. I'll see you all again soon. Goodbye.